Since my last video was so controversial discussing the difference between fallout shelters and blast shelters or bomb shelters, I thought I would go more in depth. That way we can see where the truth lies. Now, in the past, the military and the Atomic Energy Commission, Corps of Engineers, FEMA, Defense Department, and DISAC, various other agencies in the defense agencies of the DoD put out a lot of publications. There was actually a series, and I'll show you a few of those later, that are designed for professionals in the construction industry and engineering industry on how to actually build, modify, and improve buildings in order to make them either successful fallout shelters or blast resistant so they can be used as blast shelters. Now, when I was talking about flat top shelters, whether they're buried or not, they are susceptible to downward pressure. So in an atomic bomb or a conventional bomb, if it explodes above or in contact with the top of the shelter, the soil over it, you're going to have a top loading event where you're going to have a PSI overpressure. So what that PSI overpressure is, we don't know. But this particular design study was designed for a 1 megaton 1 mile away. So that detonation, what they did here is instead of steel, they had a composite steel and concrete structure that's similar to what a square-shaped blast or fallout shelter would operate and act. So when we look at this, they actually built a model. This is them building the model, and they shock loaded this. So here's more pictures of it. It gives you the footing designs, so forth, for where the posts sit down. So in this photo, you can actually see the columns and the beams and how they will sit onto the slab that's designed, and then they will top load this. And like I said, this was the equivalent of a 1 megaton weapon 1 mile away detonation. This is the layout plan, and it shows you a lot of the pressure instruments in here. And what we'll do is go over here to the test results. So that was the pressure diaphragm, which was still in place, that loaded the building. This was one of the results, and you can see the top cracking where it was loaded. And then we can look at individual cells inside of this frame structure. So if you have a welded steel structure, you're going to have a frame structure reaction also. And I'd like to point out that people a lot smarter and better at mathematics did these tests and made these measurements. And you can see how they progressively fail. This is an inside of the model. And just as I said, you have failure in the top. Now, what people don't realize is if you have a downward failure like this, your shelter is not going to be waterproof, water resistant. You're going to get intrusion of radioactive groundwater and radioactive materials from the surface. This is another view. So these are different loadings. And you can see this one was pretty catastrophic. And it goes into more detail here, different cells, how they cracked. So we can see from here that there is a definite difference between the structural requirements of a blast shelter or bomb shelter and that of a fallout shelter. Now, in another publication, I'm going to show you some interesting things about entryways and how they contribute to reduction of the dose rate inside. This Corps of Engineers document is a design of openings for buried shelters. And this was an attempt to standardize the openings so it was easy to calculate. When I was working at a power company that had nuclear sites. They wanted to increase the protection level of a building they used to screen people prior to going into a nuclear facility. So they wanted to do a blast wall. And I told them, I said, DOD and Atomic Energy Commission has all this material that's pre-calculated that you can actually use when you're designing things. And it's all been load tested. There's stuff that's been tested with actual radioactive materials. So we're going to take a look at this, and there's a very important table in here. These are just some of the geometric designs that were looked at in buildings and how to reinforce them that they did calculations on. And like I said, this is all pre-calculated material. It's been about 30 years since I did any calculations like these. So I'd have to do a lot of studying to actually go back and do the calculations myself. We used to do a lot of this by hand before there was computerization. And in here, this is a probability chart showing the distribution potential of radioactive materials, and it's in a circular pattern. So it's interesting, if you look at this, this is the same way that you would calculate the distribution of rounds on a target. So if you were target shooting and this was a bullseye, it's the same distribution method that's used to calculate bullets. So they're calculating radioactive particles. So as I was saying here, when we're looking at individual cells for radioactive particle intrusion, it's taken just from how you would analyze a shot pattern that you were shooting with your rifle. And what they're doing is basically using polar coordinates, and you can see the formula there. This is one of the most important diagrams in this entire book about entrance to shelters and how a reduction in the dose rate of incoming nuclear radiation can be determined. So here, when we're looking at this, we have two functions. We have the shelter itself reducing radiation on the right. We have the entrance system. And when you look at the very bottom line, you'll notice there's neutron, gamma, and gamma. So there's prompt radiation, and what that prompt radiation is in the initial nuclear pulse of the weapon. So if you're within the action envelope for initial nuclear pulse, you're going to have neutrons. You may get some neutron activation in materials around you, and you'll have gamma. And then residual is fallout. So you'll see there's actually 6 contributions to the dose rate you're going to get in your shelter. So the entrance system goes a huge way in lessening the total dose. So this is an important criteria in the design process. It looks like not much, but this is a critical factor that I don't see anybody discussing. Now, back in the old days, I guess, and these were published and put out until probably around 1980, and you could still get some in the 1990s. In the 90s, FEMA really got rid of all civil defense. A lot of these publications are very difficult to find, but as you can see, there's a professional guide series, and what this does is tells you how to incorporate shelters into buildings you're designing. This one is specifically for schools, and they talk about schools that are slab on grade as well as multi-story and basement. This is one for incorporation into churches. This is incorporation of fallout shelters into apartments and office buildings. And there's also guidance on blast shelter and how to harden these buildings. This is another one, older, on shelters in apartments and office buildings. And finally, another one for schools. Now, I also, in my reference material, I have ones on using ships as fallout shelters and many other things. When you get into the nuts and bolts, there's a lot of very detailed stuff about blast loading for the type of walls, debris from interior walls getting blown out, things like that. and what the blast effect of that is on humans. So as you can see here, there's a lot of information that backs up what I said in that video. So we're going to do another installment in the Nuclear War Survival Series. This is a publication put out by Nuclear Defense Laboratory of the U.S. Army. It is non-classified. They are very hard to find copies of. This is specific study in decontamination during cold weather. And there's something important in here you need to see. So they discuss what they use to decontaminate. And they used a lot of construction equipment that's commonly available. And in some of these tests, they use actual radioactive materials. In some of these, they use tracer materials. So it depends on which study you're looking at. Now, they also used water when available, but if you're in cold weather, you're going to have very limited use of water. And in here we have a pressurized slurry system where we're using a decontaminant. So you have to have some kind of antifreeze component to water when it's this cold. So now we're going to look at the important findings here. So when you're looking at these charts, this is a discussion of activity, which is a measure of radiation. So this particular one was a roof. And after decontamination, we still have contamination there. It's just not as much. So it's a reduction. So you would have a reduction in dose rate. When you look at the column all the way on the left, this is the activity level. Then we decontaminated it. And then we have activity remaining. So you can see there was quite a bit of decontamination. And the various results here, what they actually show you is the fact that after decontamination, you're not going to remove everything. So in effect, what you're doing is reducing the dose rate. So when you decon stuff, you need to take a pre-measurement and a post-measurement, and that way you can look at your dose rate charts to see whether you can work in that area following decontamination. And I can tell you for a fact, some of the studies I saw where they tried to decontaminate ships from the atomic tests, they tried 3 decontamination attempts or more, and they could not get the radiation levels low enough where they could occupy the ship, so they ended up sinking them. So in a post-disaster scenario, you have to take into account the rad levels that you're experiencing during decontamination, what your resultant dose rates are, and whether the after effect is going to be good enough where you can actually get in that area and work following the decontamination. So you really need to think about whether you can work in an area you decontaminate following the decontamination, because the dosage you're going to take doing it is going to be pretty severe. So keep that in mind. Please comment. We'll see you on the next video.